Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today we're going to talk about a common mistake that I see on interfaces that are exposed through connectors, including USB connectors, HDMI connectors, and similar connectors. And this is how to properly select an EMI filter or an EMI choke, and how to select a TVS diode for those interfaces. Now I will admit, I have made this mistake myself in the past, and this came up again when we were doing one of the 1-minute design review submissions. So we're gonna hop back into that design, take a look at exactly the components we're gonna be considering in this video, and we're gonna take a look at how to find the right parts for EMI filtering and TVS diodes. Let's go ahead and hop in and get started. Now in this video, we're going to take a look at one of the 1-minute design review submissions, and this submission came from Mustafa Gunnar. This design was for a distributed I/O tier board, and in this board there is a USB connector, and on that USB interface there is a common mode choke. There's also a TVS diode array that can be connected to both of the data differential pairs in that design. Now here I have the design pulled up on screen in 3D, and obviously you can see that there is a lot going on in this design, a ton of traces on the surface layer. And if we just go into the schematics and we open up the USB sheet, we can see here that common mode choke that I'm talking about. You can also see here the TVS diode array that's used in this design. Now there is also a ferrite bead on this ID line. There's also a ferrite bead on the V-bus line, and I'm not going to get into the ferrite beads in this video. You all know how I feel about ferrite beads, and if you want to learn more about my thoughts and what the experts think about the use of ferrite beads in digital systems, take a look at the video that is linked in the video description. Now what I want to do instead is focus on this common mode choke and this TVS diode. And these components need to be selected carefully because they are being put on high-speed data lines. Basically, when we put an EMI filtering component or a TVS diode or any other circuit protection on data lines for digital signals, we want to make sure that those components don't impact or filter out any of the digital signal content that you're trying to transfer along those lines. Now remember, a common mode choke is basically an inductive filter. It adds a bunch of inductance onto these lines, and that could impact signal integrity as you get to progressively higher frequencies. With the TVS diodes, they have some capacitances across them, and those capacitances can also filter out some of that signal. And so you can lose some of the signal power at certain frequency ranges as the signal interacts with these components. Now the first thing I want to do is take a look at this common mode choke, and I want to look at the data sheet. Now if you just take a look at the description that was put on the component in the schematic, you'll see here that it just says inductor common mode, and then here under the parameters it lists the current rating, it lists a series resistance, and then it lists a packet size. It also lists an impedance at 100 megahertz, as you can see right here under the value entry. And so you should ask yourself, is this enough information to properly select a common mode filter for use on a high-speed interface? Well, first thing we should do is actually take a look at the data sheet for this component. And you'll see here that we actually have the manufacturer part number specified. And if we go over here to the internet on DigiKey's website, you'll see here I have pulled up that component. Now here, if we go into the data sheet and we just do a quick Control F, you'll see that the word USB is not mentioned anywhere in this data sheet. In fact, if we just scroll down through this data sheet, you will see that this component has an inductive impedance that goes well above the USB impedance target at 100 megahertz and at 1 gigahertz. So in this range, you've already gone far beyond the USB impedance target. The problem is that USB can have a bandwidth that sits in this frequency range. So it is possible that components just like this can interfere with data transfer along that USB interface. So what should you do instead? Well, the first thing you should do is you should search for a USB EMI filter, or better yet, search for a common mode filter for USB. So this is really important because a common mode filter and a common mode choke are actually sometimes used interchangeably. Sometimes someone puts a common mode choke in a design when what they really need is a common mode filter, and vice versa. Sometimes you'll see a design that has a common mode filter when what they actually need is a common mode choke. And the two types of components are not the same thing. Let's take a look at this example from ST Micro. I'm just going to pull up the datasheet from Octopart. Now the first thing you'll note from this datasheet is that this component is specifically rated for use on USB interfaces, whereas the common mode choke that was used in the design was not. Now, as we scroll through this datasheet, you're going to see some very important information. Some of that information is the attenuation value for differential versus common mode signal. You're also going to see some return loss plots, and those are very important because those help you really determine whether or not this component is going to be suitable for a particular high-speed interface. Let's take a look first at the SDD21 plot. So this is a differential insertion loss plot. Now you can see here that the insertion loss is only at about negative 0.6 dB all the way up to about 300 megahertz. It then starts to fall off and go down to about negative 2 dB at about 2 gigahertz. So you've got really good transmission through this component up to high frequencies, and that's exactly the range where you want to be transferring all of the power for that USB signal. So this is the first thing you should look for. You should look for the differential insertion loss, and you want to make sure that the differential insertion loss is very low within the channel bandwidth that you're targeting. Well, the next thing you should ask is, what about the common mode noise or common mode signal? Is there an attenuation value for that? Well, if we just scroll to the next page, you'll see here that we also have a common mode insertion loss plot, or the SCC21 plot. Now what this plot shows is that it starts very strongly attenuating common mode noise or signal right around 100 megahertz, and then it gets to very strong attenuation all the way up into the 1 gigahertz range. So these two plots show you very nicely that this component is specifically designed to transmit all of the differential mode, but filter out or remove all of the common mode. Now the next thing we need to look at is the SDD11 plot. So this is a return loss plot specifically for differential mode signal. And you can see here in this return loss plot, we maintain very low reflection all the way up well above 1 gigahertz. We don't start to see high reflections until we get above about 2 gigahertz. So what do we take away from all of this? Does that mean that this component is going to automatically make every single USB interface fail? Well, at the end of the day, you should always test it. And if you want to reduce the risk of failure or eliminate the need to possibly do any rework in the design, just go for a component that is already rated for the USB interface or USB data rate that you're going to be working with in this design. Now, Mustafa's a smart guy. He put together a great design in this submission, and I have to believe that he's actually tested this and made sure that this particular component is going to work in this particular system at this particular data rate. But again, I'll repeat myself, if you want to reduce that risk that this interface functions incorrectly because you picked the wrong common mode filter or common mode choke, just go and find a common mode filter that is rated for that particular interface. Now these common mode filter components aren't just built for USB. You'll also find options for HDMI, for example. On this search on Octopart, we already have some options for HDMI, including this first one that comes up from On Semiconductor, and it lists HDMI right there in the description. And even though this component is rated for USB right there on the front page of the datasheet, you can always use the data that I showed in the datasheet to determine whether you could use this EMI filter on any other interface that you might use in your design. Next, I want to take a look at this TVS diode. Now this particular TVS diode you see is actually a diode array. It is meant to be used on interfaces where you have multiple lines running in parallel, and all of those lines need to be connected exactly as you see right here. So we've talked a lot about this common mode filter, but what about this TVS diode? Well, here on Octopart, I have this TVS diode pulled up, and you can see here I've pulled up the datasheet as well. Now here in this data sheet, you can see right here in this fourth bullet point on the first page that it is typically used on high-speed ports such as USB 2.0, this IEEE standard, SATA, DVI, HDMI, and PCI. So this TVS diode array was selected correctly. It is selected based on the actual standard that you are trying to protect. However, there are other TVS diode arrays which are general purpose, and so you need to check that they are actually going to function properly for your particular interface. Now this can actually be a bit difficult to do in terms of signal integrity, and sometimes it might require some SPICE simulation to properly determine whether or not you get too much attenuation in that signal as it interacts with that TVS diode. The mechanism by which that TVS diode will filter out or attenuate that signal is twofold. One of them is through the capacitance across that diode, and then the other is due to driving the diode into reverse bias, in which case it then starts to conduct some of that signal towards ground. Now the reverse bias spec is easy. You can look that up right there in the data sheet, and that's usually the first thing that people look at when they're selecting, well, really any diode. Now the capacitance is also given in the data sheet if you have a diode that is suitable for use on a high-speed interface. And in fact, you can see right here in the third bullet point, it says low channel input capacitance of typically 1 picofarad. Now, if we scroll down here in the data sheet, you will see that there is a total capacitance curve as a function of reverse voltage. We would like for this total capacitance curve to be relatively flat over that full signal range that's going to interact with this TVS diode. So just to summarize what we're looking for if we're going to qualify a TVS diode for use on a high-speed interface. We want low capacitance, and we want to make sure that the reverse voltage is larger than our signal voltage. It also helps when you have a part like this, which is specifically tested and rated for use on the high-speed interface that you're working with. Now, as I mentioned earlier, I have messed up in the past when selecting these types of circuit protection components, and one of the projects where I originally did that was in the USB to UART bridge project that we did here on the channel. Now, I've since corrected that mistake by selecting an appropriate TVS diode for these lines coming off of the USB connector. But when I originally did this project, the part that I selected was not rated for USB and would have been going into reverse bias at a low voltage. So that was pointed out to me by a viewer, and I've since corrected that in these project files. But let's take a look at this part number. Here you can see I have the datasheet pulled up from Texas Instruments. It says right here, VBus pin and ID pin of the USB ports and general purpose I/O ports. You can also see that it says the 12 picofarad line capacitance of this ESD-protection diode is an excellent choice for a wide range of applications supporting data rates up to 400 megabits per second. Now, in addition to mentioning the data rate and mentioning USB specifically, if we just scroll down in this data sheet, you'll find some of the technical data, and then you will see here the insertion loss as a function of frequency. You see that it starts to roll over a little bit before 1 gigahertz, but still at high enough frequency to support a USB 2.0 interface. You can also see again that this capacitance is a little high, but it's not so high that it's going to negatively impact the functionality of a USB 2.0 interface. Now, as I mentioned, I have updated those project files with the correct TVS diode. So if you take a look at the link in the video description, you'll be able to check out the original video where we go through this design, and you'll be able to get access to those project files. Thanks for watching this video, everybody. Make sure to hit that like button, hit the subscribe button, leave your comments and questions in the comments section, and last but not least, don't forget to call your fabricator, folks. We'll see you next time.